Hey, welcome back, everybody.
That's okay.
A session with Arjun Suresh from New York University, who's going to talk to us about radio AGN in low redshift galaxies. Sorry.
Okay, thank you. My name is Arjun Suresh. I'm a PhD student at New York University working with Professor Blackton. And today I talk to you about some of the work we've been doing with AGN. And the title of the talk reads Radio AGN in Low Redshift Galaxies, hopefully legal comparison between observations and simulations. The structure of the talk will be as follows. In the beginning, I'll lay down the aim of this project. And the aim of this project is to test the theoretical AGN feedback models against observed AGN host relationships that are reliably measured. And then I'll talk to you about some of the gaps in the existing observations of AGN host relationships. And I'll go on to talk about how we try and fix those gaps in our actual observational work and derive observational reliable constraints between AGN host relationships. After which I'll talk to you about testing simulations such as Illustrious, TNG, Simba, and Eagle against the constraints that we derive from our observational studies. So let's start. This has been touched upon in the introduction in the beginning, so I'll keep it brief. So simulations require AGN to suppress star formation at high stellar masses. And nowadays, the simulations are able to successfully reproduce the observed galaxy stellar mass function. However, it is important to recognize that they're able to do so because they are specifically tuned to be able to do so. To truly test the underlying physics of these AGN subgrid models, it is important to conduct independent observational tests of the models. And we devise one such test, and we test the models by coming up with reliable measurements of AGN host relationship. So there are existing AGN host relationships measured, of course, but a lot of them are unreliable, and mainly because they use host galaxy properties that are poorly measured. Most of the studies use single fiber observations for their host galaxy properties, which doesn't give enough precision to be able to reliably constrain the host galaxy and AGN relationships. Another reason is the detected AGN host relationship could be vastly different from the true AGN host relationship of the entire underlying sample. It's hard to reliably account for these relevant flux and star formation rate related selection effects, and a lot of highly cited studies in the past struggle from these issues. So the long-term goal of our project is to measure the AGN host relationships while accounting for the relevant selection effects for the various manifestations of AGN, such as radio AGN, broadline AGN, narrowline, mid-IR, X-ray, etc. However, we've done some progress on radio AGN so far, and that will be the focus of this talk. So yeah, you've seen this plot picture in the morning. Just to define what I mean by radio AGN, AGN come in two flavors: radiatively efficient AGN, which are usually not bright in the radio, and radiatively inefficient AGN, which where the bulk of the energy output is in the form of relativistic jets, and they're usually bright in radio because of synchrotron emission due to these highly relativistic particles. So in this project, we will probe these radiatively inefficient AGN via their radio emission. Again, this is something that was touched upon in the morning. One of the main motivations for this theoretical picture that radio AGN are involved in suppressing star formation rate comes from joint X-ray and radio observations of massive galaxies in nearby clusters, where these bubbles, these cavities show the interaction between jets and hot gas in the galaxy atmosphere. And in theory, this AGN energy can couple with the gas and keep the gas from cooling down and forming stars at the center of the galaxy. In addition to that, what adds to this theoretical picture is that these massive galaxies that are not forming stars are also the ones that are most likely to host radio AGN. So in this plot on the lower left, we can see that the radio AGN fraction is a very strong function of stellar mass. And furthermore, a plot you've also seen in the morning, there is good correlation between the power needed by the AGN to create these cavities and the energy lost by the gas due to radiative cooling. So all of these observations have together sort of given rise to the theoretical picture that radio AGN feedback is involved in suppressing star formation at high stellar masses. So that's the theoretical picture. However, that picture has some gaps. For example, there are no reliable observations of how this AGN jet energy couples with the gas. So we don't know the physical mechanism of this coupling. And as I've already mentioned, there are no reliable measurements of the statistical correlation between AGN feedback and specific star formation rate, SSFR. Previous studies have relatively low precision determination of these involved quantities, stellar mass SSFR and velocity dispersion sigma, and they do not account for the relevant selection effects. So the aim of this observational study is to measure the Eddington ratio distribution of radio AGN, accounting for the flux and star formation rate related selection effects, and to see how that distribution depends on host galaxy stellar mass and specific star formation rate SSFR. And here, by Eddington ratio, I mean the ratio of the power in the jets or the cavities over the Eddington luminosity of the black hole. Right, so to do this project, we make use of the Manga optical IFU catalog, which provides us with high signal to noise observations of around 10,000 galaxies in the local universe. So it provides us with multi-fiber spatial resolution of each one of those galaxies. So as opposed to the historic single fiber measurements of galaxies, we get much more precise determinations of the relevant quantities such as stellar mass, velocity dispersion, and SSFR, specific star formation rate. And these are some of the best available determinations of these quantities for a statistically significant sample. So we take the Manga catalog and we match it with the NVSS and FIRST radio catalogs, and we match them down to 2.5 millijansky as opposed to the previous 5 millijansky by Best et al. 2005. And going to 2.5 millijansky gives us about twice as many matches for the Manga sample. So we provided this catalog as part of the paper. So if you want to use the catalog, I encourage you to do so. These are some images that we saw while matching the catalogs. I just thought I'd show them. Okay, so once we match the three catalogs, it allows us to make a plot that looks something like this, where on the y-axis we have the radio luminosities of these galaxies, and on the x-axis we have the host star formation rates measured by Manga. And immediately we see that the plot sort of automatically divides itself into two distinct clouds of points, where there is a well-correlated cloud of points at high star formation rate. And this is possible because of the high precision measurements of Manga. So because of this, we can introduce this star formation rate dependent cut as indicated by the gray line, and call only the galaxies above that line as detected AGN. And this is a much cleaner sample selection than the previous Best and Heckman 2012, which has a very complicated sample selection function. And such a simple sample selection function allows us to impose upper limits on the radioluminosity and to model them quite straightforwardly. So I said there is a small subset of the Manga sample that are detected radio AGN. That doesn't mean that not the rest of the galaxies do not host AGN. It could be that they do host AGN, but just ones that are too faint to be picked up given NVS's flux limit. So the basic ansatz of this observational paper is that all galaxies are AGN, but we only detect some. They could be AGN of arbitrarily low activity. So for these non-detected AGN, we impose upper limits. and we use these upper limits while modeling the radio emission of these AGN. Right, so very quickly, we take these radioluminosities for the detected AGN, and we take upper limits on the radioluminosities for the non-detected AGN, and we convert them into Eddington ratios using this scaling relation from Cavagnolo that goes from radio power to X-ray cavity power. And we convert the manga velocity dispersions into black hole masses, and we get lambda Eddington ratios and upper limits on Eddington ratios for all the manga galaxies. So now we have the manga sample, a bunch of them are detected AGN for which we have measured lambdas, and the rest of them are non-detected AGN for which we have upper limits on the lambda. And to this data, we fit two separate models for the Eddington ratio distribution. The first model depends only on the stellar mass of the host galaxies, and the second model depends only on the SSFR of the host galaxies. So we fit these two models, and based on the best fit models, we generate Monte Carlo data sets and as a method to sort of evaluate these models against each other and against the observations. So one of the tests we carried out after fitting these models was to just apply the selection effects to the model and compare the detected AGN fractions against the observations. So in this plot on the top panel, on the y-axis, we have the detected AGN fraction, and on the x-axis, we have stellar mass and host SSFR. The black circular points correspond to actual observations, and the gray hexagonal points are predictions by the M-star model. And immediately we see that the M-star model is very good at predicting the trends against both itself and against SSFR. In particular, it is impressive that it predicts the trends against SSFR having no explicit information about the SSFR of the host galaxy. In stark contrast to that, the SSFR model, though does quite well against itself, it fails to predict the trends against stellar mass, especially failing at low stellar masses, where it predicts too many AGN relative to the observations. So based on that plot and a bunch of other plots that we show in the paper, we interpret the following. As expected, the radio AGN Eddington ratio is a strong function of host galaxy stellar mass. And at fixed mass, the radio AGN Eddington ratio distribution does not at all seem to depend on the SSFR of the host galaxy, which is a new result. I don't think we've seen this before in the literature. And these constraints allow for reliable and easy comparison to the simulations. So we evaluate our M-star model to sort of specify it in a way that that's easy to compare to the simulations. So we evaluate what's known as the absolute AGN fraction, which is the fraction of AGN, the fraction of galaxies in the universe that we expect to be radio AGN, irrespective of if they're detected or not. And we provide that fraction as a function of host stellar mass above some Eddington ratio cut of 10 to the minus 3. So this is a robust specification of our M-star model. And notice that this plot encompasses both the constraints that we found out in the previous slide. It encompasses the strong M-star dependence, and it also encompasses the SSFR independence, because there's only one line. Or in other words, if I split up this line into star-forming and quiescent galaxies, they would sort of overlap each other up to some small precision. Just to illustrate why it is important to account for these selection effects, if we naively just looked at the distribution of detected AGN, we would have incorrectly concluded that the FAGN dependencies against stellar mass are different for quenched and star-forming galaxies. And we would have concluded something like radio AGN are preferentially found in quenched galaxies, which has been concluded before in the past, but as we've shown, that is not really true. So now we have this constraint, and we compare simulations to this constraint. And as you all undoubtedly know, simulations rely heavily on subgrid models, among other things, because they don't have the resolution to be able to resolve what the AGN is doing. These AGN feedback models vary significantly across simulations, even though they sort of serve the same purpose. For example, the illustrious TNG model has two modes of feedback, one for the high Eddington mode, one thermal mode of feedback for the high Eddington mode, and a kinetic mode of feedback for the low Eddington mode. The Simba model has also two modes of feedback, both of which are kinetic, but Eagle has only one thermal mode of feedback that is sort of supposed to mimic both of those based on the Eddington. Right, so we now evaluate these predictions by these models, and so these fractions for the models are uh, correspond to what we think are similar to the observations, where it corresponds to the radio mode and above the cutoff of 10 to the 3 minus 3 in the ratio. And immediately we see that basically none of the three models get either of the constraints right. They don't get the strong stellar mass dependence right. Neither do they get the SSFR independence right. And I mean, importantly, the stellar mass dependence has been known in the literature for about 20 years, and yet somehow these simulations don't get that right. Just briefly, I'll talk about the illustrious TNG model specifically. So illustrious TNG has this transition Eddington ratio that is dependent on the mass of the black hole. And below this transition Eddington ratio, the black hole operates in the radio mode. So in this region below the gray line, the black hole operates in the radio mode. And you can see that only galaxies that have these radio mode are quenched galaxies, and galaxies above, none of the galaxies above that are quenched. And this is the default model of illustrious TNG. And we see that the default model doesn't really get the AGN number of AGN right. So we just wondered if it's worth sort of tweaking the model, the parameters of these models, and see if we can get the model to agree with our AGN constraint. And the answer is yes, we can tweak the given model fairly, like a fair amount to be able to match our FAGN constraint. However, in doing so, we will inevitably have to alter the GSMF, the stellar mass function that illustrious TNG predicts, because now that this transition line has been moved down below, the galaxies that are in this yellow ellipse, there is a chance that they no longer get quenched because they will no longer have radio AGN, and that will alter the galaxy stellar mass function. This was we touched upon in the discussion session. Right. So I'd love to know what people have to think about this plot, and if it is at all useful to do something like this, and like, is it at all informative to make a comparison like this, and yeah, if the simulators that will find this helpful or useful. Right, so I'll just summarize. Just to summarize, it is necessary to account for the selection effects to make reliable observations of AGN host relationships. And when we do that, we find that at fixed stellar mass, radio AGN activity is independent of host specific star formation rate, which is a new observational result. We have tested the simulations against our observational constraint, and we've seen that basically none of the simulations in constraint in question agree with our relationship. And yeah, we encourage you guys to use this constraint and even the catalog if you think it will be helpful. Thank you.
Yeah, great talk. That's bold to make a, if you go to the last slide, a prescription suggestion, and I think that's great to do. One thing that we know about Lester's TNG is that the black hole masses, is the distribution of black hole masses themselves, usually match the observations, and you have like very few low mass black holes that kind of like they grow via quasar mode to like 10 to the 8, and they transition suddenly to mode and have different growth. So like, I mean, in the real universe, you might definitely have a different distribution of black hole masses. So would you recommend, like, I mean, that will change your Eddington ratio as well. Would you recommend also maybe like a prescription to alter how the black hole mass, stellar mass relationship is implemented TNG?
I don't know. I don't think I'm in a position to recommend anything. My understanding is that TNG gets the M star black hole relationship, right, or does it not?
I would argue not.
Okay.
But that's a point. Yeah, let's talk later. Yeah, it's great to have a proposed transition on this.
Okay.
But I think it's also important to think about the black hole mass as not necessarily being right in that. So
Okay. Yeah. Thank you.
I was just wondering about the comparison from observations to simulations, whether the axes are defined in the same way. For example, for the stellar mass, if the same aperture is used, and for the Eddington ratio, I think you use the cavity power and that's projected, right? So do you go about it in the same way in the simulations, or do you use the nuclear Eddington ratio?
So in the simulations, we just use the amount of energy that's coupled to the galaxy, just amount of energy that's coming out of the black hole that's coupled to the galaxy. And yeah, we don't really do much after that, and we just compare them directly to the cavity powers. And I'd be open to do anything else that you think is a better thing to do. And there was another question.
Oh, the stellar mass, they're same aperture.
For the simulations, I think it's like twice the effective radius, and for the observations, I'm not really sure if it's the same. Yeah. So yeah.
The observations is SDSS.
This is manga. Yeah.
Yeah. So like 3 arc second fiber.
No, it's manga, so it's the whole galaxy.
Yeah. 3 arc second.
So it's
The fiber is of 3 arc seconds, I think. The stellar masses are still from NSA, there's NASA catalog.
No, manga also has like stellar masses that they use. They use the spectra to fit.
And they took those and not the ones from NSA.
Correct, but they agree with the NSA.
Okay.
Stellar masses, yeah.
So you made the selection for your sample purely based on the radio density?
Do you mean the observed sample?
Yes.
Yeah, based on luminosity.
Yeah, so I was curious, like, because there are also radiatively efficient AGN which have radio jets, right?
Yeah.
So is this like, do you know for sure that this is a clean sample of radiatively inefficient AGN, or is there actually just like a mix of different?
Yeah, we're not really making
This is happening.
Yeah, we're not really making that distinction really. But if previous studies are to be believed, in the manga sample, the radiatively efficient radio AGN will be a very small subset of the radiatively inefficient ones. Like the lurgs will tend to dominate the lurgs.
Yeah, because you found like some of them were in star forming galaxies where some of them are quiescent, and I wonder if that could be related to, the host galaxies are related to whether they're radiatively efficient or inefficient AGN.
But at these stellar masses, at these the highest stellar masses, we don't really have star forming galaxies, right? Like we don't have galaxies that form stars at
Oh, I thought you had a plot where you were showing that some of them were star forming, but maybe that was that the simulation? Sorry.
Which one?
This one.
Yeah, this one.
No, these were detected AGN, but at these the very high masses, there aren't really
Yeah, but I meant the things that are in the blue galaxies and the star-forming galaxies. Are these more likely to be radiatively
I see.
efficient things with radio jets?
Yeah, I haven't looked into that, but that's something worth looking into. But they're still sort of half a dex below. These radiatively inefficient agent might still tend to dominate.
I think today, so we've done similar things with Lofa. We find that yes, the radiatively efficient radio AGN seems to be the galaxies, but there's something interesting that's happening, and I think you can investigate really well. And it's the fact that we do see a fraction of radiatively inefficient things in galaxies, and this is probably related to where the gas is. However, you have gas in a galaxy that can make stars doesn't mean that that gas has already made its way into the black hole, or maybe it has, and then there's been that has quenched, has starved the AGN of gas. If you have manga data, I was wondering whether you are looking to investigate the dynamics of the gas, particularly in these gas-rich samples, gas-rich galaxies, to see, where the gas is distributed for them, what the AGN is doing. See what the connective links are in.
Sure, that sounds like an interesting thing to do. Would you know what the fractions are of radiatively efficient AGN in?
So far we go much deeper. It's a factor of 10 to 100 deeper than first and MBSS. So we see a very different subset of the population. And there is a sizable fraction. I don't have the numbers in my head. I can look them up. There is a sizable fraction of things in star-forming galaxies. There are lurks, but you do require the gas to have a radiatively efficient AGN. So it's incredibly rare that in one of those quenched galaxies you will have a radiatively efficient AGN. Having the gas doesn't happen. But there are different samples.
Very quick one. I just was wondering, in your AGN definition plot, radioluminosity versus star formation rate, what was your reasoning behind this horizontal cut? Why are you excluding from the AGN sample lower luminosity sources in passive galaxies?
Yeah, mainly because at these lower star formation rates, we weren't sure if things could scatter into, like, star forming galaxies with imprecise measurements of star formation rate could scatter into the AGN sample and contaminate the sample. Since we anyway have upper limits on everything, we thought it wouldn't hurt to be slightly conservative. And we have made this cut where we just have a straight line. We don't really change the. Yeah.
I also ask a question about the comparison between models and observations. So you did show the TNG results, and the TNG passive. No, if you back, if you can. And yes, here. So the TNG passive also only has constraints up to that stellar mass, right? It doesn't extend to very massive stellar masses. Although in one of your next plots, you saw that TNG radio mode does operate all the way to the highest stellar mass. So I'm just wondering, why don't you have any measurements from the TNG extending all the way to?
That's because of the cut we've made. So if we recognize that the absolute scales of activity are different in the observations and simulations, and we allow for that, those will tend to appear.
Okay, so it's your LC cut that you apply in the data, you also apply in the simulations. All of them are below that limit. Okay. Okay, if there are no questions, we can go to the next speaker.